So now we're going to see how we can do this that we saw on the previous lecture, how we can do it in practice in TensorFlow. So I'm going to talk a bit about basic types and then give you some examples implementing logistic regression with a training using backpropagation, and then these classical problems, the OR and the exclusive OR, where we can solve with one neuron or we need more than one neuron. So basically this is what we're going to do in the tutorial this week, and I'm going just to give a brief overview of how to implement this. So TensorFlow computations are defined in a graph, which TensorFlow creates by looking at the different operations we are using with the tensors. Each node is an operation that we are using, sum, sigmoid, multiplication, something like that. And joining these operations in the graph are the tensors where the data is going from one operation to the other. With eager execution, which is the default now on the recent versions of TensorFlow, your program will be executed like it's natural in Python, which is each line you get the operations are executed. TensorFlow can execute them on the CPU or the GPU if you have that version installed. But alternatively, you can start by creating the whole computation graph, and then TensorFlow can optimize the distribution of the operations between CPU and GPU and execute the graph. So we're going to see this better next week. Now we're going to use only eager execution, but this would be not for this course, it will not be necessary, but if you end up working with this and want to optimize the training of the network and you have good hardware, it may be a better approach, because if TensorFlow has the whole computation graph, it can distribute, for example, between different graphic cards and allocate memory better and things like that. So let's start with a very simple example. We want to compute total equals to a plus b, where a is 3 and b is 4. We can create these TensorFlow objects, these constants, and we can create this operation to add both of them. So this would be the computation graph. We have these two operations, these two tensors here, and we have this operation of summing them, and then we obtain the result of the operation. So this total is the result of this sum of the two constants there. With TensorFlow 2 onwards, the one that we'll be using, if you execute this, you get immediately the result. So you see total is a tensor. It's just one number, so it's not, it doesn't have any size there. And it has this attribute here, which is the NumPy object corresponding to that tensor.
In the code example, you didn't define the type of B. So A is defined as TensorFlow float 32.
Yes, and this gets the default. So probably this is floats 64 or 32, depending on where what the options you have. So you don't have to assign these types. If you want to optimize things for GPU, then the float 32 is ideal. Otherwise, you can just let it decide. So if you don't want to specify this, or if you're using CPU, you don't need to be very careful with that. But I think if you're using GPU, this will be the default float 32. I'm not sure, but in any case, you can specify that. So if you want to increase the graph, you can say, in this case, we are multiplying by this C. So now we have this result here, and so as you keep adding these operations, you keep creating a larger graph. This is what TensorFlow can create if you use deferred computation. If you create the whole graph first, and then it knows what all the operations are and how they fit together. If you just run it as default, it will do everything step by step. So if you want to obtain the actual value there. So note that result here is a tensor object. It has all of these different attributes. If you just want the number, you can use the numpy method there, and it returns only the value that it has. In this case, it's a scalar, so it's only a number. If it's an n-dimensional array, it will return the numpy object for that array. So let's use this to implement logistic regression with TensorFlow. What we are doing here is creating a function of some parameters that uses this logistic function here, and it takes a linear combination of the features. It adds this bias value, and then 1 over 1 plus e raised to minus that linear combination will be a value that ranges from 0 to 1, and which we can interpret as the probability of an example with these features belonging to class 1. So logistic regression is a regression because it tries to adjust this probability function, which is a continuous variable, but we use it as a classifier if we determine a threshold here, for example 0.5, where we can separate one class from the other. If the probability of being in class 1 is over 0.5, we classify it as class 1. If it's below 0.5, we classify it as class 0. So we do this by solving for the parameters in order to minimize the logistic loss, which is this function where you have the sum for all the examples of the target value. This is the class of the example. It can be 0 or 1, multiplied by the logarithm of what we are predicting here. And then, so the output of this logistic function. And adding 1 minus the target value and multiplied by the logarithm of 1 minus this. So the idea here is that if the class is 1, we are using the logarithm of the probability in this term here. If the class is 0, we are using the logarithm of 1 minus the probability that we find here. So we are trying to minimize minus this. So basically, we are trying to make it so that our predicted probabilities are as close as possible to the actual class labels that we have. Okay, so now to implement this, we need to create the computational graph for this part. So this is the graph here. We have a set of weights. I have an amplified version. We have a set of weights, these here, that we start with a random normal distribution. We have this bias here that we can start at 0, and then we input our data here, the x. So basically we are doing a matrix multiplication between the weights and the data. The data can contain several examples. Then we add the bias, we obtain this net value here, and then we keep going through all the loss function, the output of the sigmoid, and so on. So this would be all of these logarithms going all the way to our final cost function. So if we write all of these operations in TensorFlow, TensorFlow will understand what the computational graph is. It will also have all of these parts for the gradients, the corresponding gradients of all of these operations, and that is what it will enable it to do the optimization. Okay. So I'm not going to show all of these graphs, but all of these operations have the corresponding gradients so that it can compute, do the automatic differentiation when we are trying to fine-tune the parameters. So let's see the starting point here. We're going to load this gene data. I think I have, it's this one here, this kind of data. We're going to separate the class labels, which are in the last column of our file, our matrix. The two features, which are the coordinates here, are the first two columns. And so we are then going to standardize the features. The class label we don't standardize, it's 0 or 1. But the features, it's a good idea to standardize so that they have the same scale and they are around 0. To do that, we're going to compute the mean in the first axis. So remember from NumPy what this does. We have this matrix here. We are computing the mean in the direction of the first axis. So it means going along the rows. This gives us a vector with two values, the mean of the first column and the mean of the second. The same for the standard deviation. And if we now subtract this vector from the matrix, it will broadcast through all the rows. So it will subtract the means from all the rows and then divide by the standard deviation vector. So this means that after these lines, we have a matrix of values that all the columns are centered at 0, have a 0 mean, and all the columns have a standard deviation of 1. So now we're going to create our little neuron. We're going to create here a global variable called weights. This is a TensorFlow variable. This is the initialization. We're going to use the normal distribution. And this is the shape of the variable. It has 2 rows and 1 column. It's a tensor with 2 rows and 1 column. This is so that we can do the matrix multiplication with the examples that are coming 1 example per row, like I showed you on the previous lecture. The bias value is the one that we sum. It can start at 0, and we can give names to this. So I'm not going to show yet what these names are for, but basically if you tell TensorFlow to compute the graph and show the graph here, you can see the names appearing on the graph if you give it the name. So these are the weights, the bias, because I gave them those names. And now we're going to create a function that, given a matrix of features for a set of examples, will give us the prediction of the classes for those examples, or basically the probability of belonging to class 1 for each of those examples. So to do this, since this can be a NumPy array, we're going to create a tensor object using this NumPy array as a constant. So I'm going to typecast it to float32. I'm going to create this tensor object with the data that it's being presented here. And now we're going to compute this function here. So first, a matrix multiplication with between the matrix of examples and the weights, which is this column here. And as we do this matrix multiplication, we get a column with all of these products of the weights of our model and each example for all the examples in the matrix. And now we can add to that the constant, the variable, the value of bias, and this will be a column with all the values for this expression here, for all the different examples in the matrix that is presented. And now we do the sigmoid. We apply the sigmoid activation function, which is this part here. So 1 over 1 plus e raised to minus x is the sigmoid function. We just apply that and we get the result, so this curve here. So this is how we implement the function for the prediction. Note that we are using all of these operations from TensorFlow because we need those objects so that TensorFlow can keep track of all the computation. Now we need to compute the loss. This is the loss function here. This is the predicted probability. This is the actual label for each example. So the loss function will be, let's assume that the predicted probability is a vector, is a tensor with 1 dimension, which we obtained here. So we applied this sigmoid activation function to this tensor here, that is a 2-dimensional tensor with 1 column and 1 row per example, for each example. But then we reshaped this so that it's a 1-dimensional vector. Now this is a bit tricky because when you are doing this with the tensors, you need to take care that they all match correctly with the dimensions and so on. When we start working with more complex networks, we will be using cache, and so you no longer have to worry about these details because they are all hidden in the API. But this is just to show you how things are working under the hood. So the output of the prediction is a tensor with one dimension and as many values as the examples we presented to this function. So this vector will give us the probability of belonging to class 1 for each of those examples. Now, the logistic loss will have to compare those predictions, which are a TensorFlow object, with the actual labels that we got from the file. And these may be a NumPy vector. So we're going to start by creating a TensorFlow object from this data here, so that we can now apply these TensorFlow operations to implement this logistic loss, comparing the predicted probabilities and the target values. So basically, this is what we have here. We're going to compute the mean, which is this part here, the sum divided by the number of examples, and it will be the product of the class labels multiplied by the logarithm of the prediction, plus 1 minus the class labels multiplied by the logarithm of 1 minus the prediction. And then we're going to return this value here. So there is a minus sign there, which is this minus sign here. And this would be the loss function that we have. Okay, so now that we have the prediction and the loss function, we need to put autodiff to work to get us the gradients that we need for the optimization. So we must tell autodiff to keep track of all of these operations and then to find the gradients with respect to the variables that we want. And this is done in this way. We create a gradient tape object, and in the context of the gradient tape object, this tape object here, we are going to run through the whole computation. So we have an array of features for a set of examples. We have the corresponding labels, and we're going to pass them through our neuron. So we're going to compute the prediction for the probabilities of belonging to class 1 for all of these examples. And then we're going to go through the logistic loss by comparing this prediction with the actual class labels. And this is done in the context of the gradient tape, which tracks all of those computations and keeps track of all the corresponding gradients, and then we'll go backwards to compute the gradients with respect to the variables that we want. So the first step, the gradient tape follows all the computations, computes all the intermediate values it needs, and then when we call this gradient method here, we tell it we want the gradient of this value, so the value of the loss function, with respect to these variables here. And these are global variables, remember, that we created in the beginning. So since gradient tape followed all of these operations with the weights, the bias, and then the comparison here, it follows all the computation graph. Now it can compute the gradient of the loss function with respect to the variables that we have here. So in this function, to get the gradient, we receive a set of examples. In the x matrix, the features, in the y vector, the labels, and then compute all the gradients and return the gradients and the variables we used. Now this is a bit redundant, but I do this so that I don't make a mistake, because if you order incorrectly the gradients and the variables, then things won't work, because then when you apply the gradients, you apply them to the wrong variables. So this way I guarantee that I put the same order in the variables that I have here. And this is how we can train. Let's create an optimizer object. This optimizer is the one that's going to use the gradient information to actually update the weights. And in this case, it's going to use a learning rate of 0.1. So basically, it will multiply the gradient by 0.1 when applying to the weights. I'm going to use a batch size of 1, just put one example at a time, but you can change it if you want. This is the number of batches per epoch, which is the shape divided by the batch size, how many epochs I'm going to do, and then I shuffle all the data, and I create, then in this loop, I'm going to present each batch by using this. I'm going to keep incrementing this start variable by using the current batch number multiplied by the batch size, and then slice the arrays between start and start plus batch size. So I'm going down the list of examples I have, and since I shuffled everything first, I have this in a different random order on each epoch. So now I'm going to call this grad function here that is going to track the gradients, and I obtain the gradients and the variables. Now this is matched because I took care to put here these variables in the same order as I gave them to the gradient method in the gradient table. So now I can call the optimizer, the stochastic gradient descent optimizer, to apply the gradients to these variables. And what I need to present here as an argument is a list of tuples with the gradient and the variable, gradient, variable, and so on for each variable. This is why I'm using zip. So I take a list of gradients and a list of variables, and zip in Python creates a list of tuples by taking in order the first element of each list, and then the second element, and the third, and so forth. So this is why it's important to guarantee that we have the same ordering here, otherwise things will be messed up. But this is the general idea. Take a small batch, compute the gradient using that batch, and then apply to the variables that gradient, so that using this learning rate, we adjust a bit the parameters on that set, on those variables. And then we do this for all the batches until we reach the end of the epoch. And then we go back, reshuffle, and do as many epochs as we need to train this. So now we can, after each epoch, we can compute the predictions for the whole set of examples and compute the loss for the whole set of examples. So this gives us the training error, the average loss for all the examples that we have, and we can do this for every epoch to see how the network is learning. And this is the result here. So this is the training error, the average loss for all the examples. It's going down as I increase the epochs. Actually here I'm using 50 epochs instead of 20, but otherwise it's the same thing. And this is a representation of how the neuron is learning during that process. Okay, so this is for one neuron. We can use this to solve the OR problem. So basically, we can use the same code. The only difference is that instead of loading this data set here, we're going to create an artificial data set with the OR problem, which is this part here, where we have true, 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 or false. So if it's true and false is true, true and true is true, true or false or true is true, and only false or false is false. So these are the two classes, but basically the code is the same. We have the same model, these two weights and the bias, the same function for the prediction and the loss. In this case, I changed to mean squared error loss. This is not a very good loss function for classification. We're going to talk about that later. But this is just to show you that you can mix and match however you want. So in this case, we take the predicted probability from the prediction, and we take the class, and we're going to minimize the square of the difference between the two. So this is another function that will be smaller as we approximate the value that we want. This is not as good as the other one because of the shape of the function, and also in theory the other one corresponds to the maximum likelihood for this kind of problem when we are trying to estimate the probability. This one is more used for regression problems in general, but it also works in this case because the minimum happens to be on the same place. And this is just to show you as an example of how you can adapt these things. So now this is the same thing. We are using the gradient tape to track all of these computations and then compute the gradient. And now one difference is that we need a lot more epochs because we have a lot fewer examples. Remember that in this case, one epoch is one pass through all these examples. In this case, one epoch is one pass through only 4 examples. So we're going to need more epochs until the network learns, about 1,000 epochs to reach here. But the idea is the same, and this one is easy to learn. Now, if we want to do the exclusive OR, we can just change here. So instead of having these labels, false or false is false, and the rest is true, we can change the labels here, and so that true or exclusive or true is also false. So now we have this different problem that cannot be solved with a linear classifier. You cannot draw a straight line that separates these two classes. And now you can see that our error is stuck here, and one reason I use the mean squared error for this example, even though it's not very correct for classification, is that it's easy to interpret here. So 0.25 is the square of 0.5, which means that basically it's not getting anything right. It's only doing as good as it would be if you were to toss a coin or guess at random. Because it's not possible to separate this correctly with a linear classifier. So what can we do? We can extend this. A simple logistic regression can work with linearly separable data. If we have more complex problems, we cannot do this. So if we apply the same algorithm, the same implementation to this kind of problem, we cannot solve it. But we can, with a neural network, solve this. We saw previously. So the idea now is to add hidden layers. This hidden layer will create a new representation of the data because one of the neurons. So if you think about this problem here, you can imagine that we could, for example, separate here and separate this red one to one side and the two blues and the red one to another side. Or we could, for example, separate here, this blue one to one side and the others to another side. Neither of these solutions would help solve the problem by itself. But if we do this in two different neurons, which are these two, so one of them will put these 3 points here to the right, to the left, and this other point to the right. The other one will put this point up, and these other 3 points down. So none of them can do the separation correctly. But when this one is looking at this representation, it's very easy to separate the two. And this is the idea of stacking these nonlinear transformations. So now we can implement this. We have the data here for the exclusive OR. Now we create one additional hidden layer with 2 neurons. And this is what happens during training. So this is the representation created by the 2 neurons. I'm not going to show the code for this one because this we'll have to do in the tutorial. But you can also see that we have these 2 stages here where we start by learning a good representation there, and then the final neuron quickly finds the best cutting point here. But the whole thing is being trained at the same time. So before at this stage, we don't have a good representation there. The last neuron cannot solve the problem, and things go a bit slower here. But then, once these are properly organized, the network takes the next step very quickly by just adjusting the final one. So, what happens when we project backwards through this transformation is that we have this separation here. And this you can do because you are putting one additional layer to do this kind of transformations. So to sum up, we saw the basics of TensorFlow. We're going to start by doing some exercises with this. We already saw one activation function, the Sigmoid activation, how to create the predictions, the loss function, how to use gradient tape to track the computations, and then give us a gradient, and how to use the optimizer, where we give the gradients and it adjusts the parameter. You're going to do this week, you're going to follow this lecture, try to solve the exclusive OR problem, and you can expand this to the multi-layer pattern we saw in the previous lecture with more layers, and then work on the other data, more complex data set. And then you can experiment with momentum, with different learning rates, because here in the stochastic gradient descent optimizer that you create here. So when you create this optimizer, if you look at the documentation, you have several options here. So you can experiment with them, momentum, different learning rates. You can experiment with master of momentum, change the batch size, and so on. So that will be the plan for this week for the tutorials, which start on Thursday. So there are 2 on Thursday and 1 on Friday. Okay, so this is the plan for this week, and we can get to the questions now.